Now, picking up with where we left on the last one, now we want to solve the recurrence relation that we just looked at along with an initial condition. The danger here is applying that initial condition too soon. You want to apply this only after getting the general solution to the non-homogeneous recurrence relation. Okay, we do now have that. We have that an has to be of the form alpha times 4 to the n. That was a homogeneous, an super h, and then minus 2, that was an super p, the particular solution. So whereas where alpha ranges over all real numbers, that gives us all solutions of the recurrence relation, and here I'm talking about the non-homogeneous one. So now that we have that, we'll apply the initial condition. So we have a0 is equal to 8 would give us 8 is equal to alpha times 4 to the 0 minus 2, and solving that gives us alpha is equal to 10. So now we have the solution an is equal to 10 times 4 to the n minus 2. Okay, so that's not too big a deal, but you do have to wait until you get to that general solution of the non-homogeneous equation before you complete it. Now here's another one where the homogeneous part, just taking that right there, an will be alpha times 5 to the n. So that part's easy. First order again. The non-homogeneous part is the minus 16n. So if we write this as we did before, it might look something like this. Put the sequence parts on the left and the non-homogeneous part over here on the right. This is not required in the solution. I'm only doing this to give us a chance to think about what might work out here. Well, the last time when we had a constant over here on this side, we tried a constant sequence. But this depends on n. And so what we'll see works out on this, and I'm going to just demonstrate this through the example, is that when that is a polynomial, as this is, a first-degree polynomial, then an arbitrary first-degree polynomial is the type of thing we should try there. So in this case it's linear, so we will try first order, first degree poly, and the polynomial would have the form let's use a c plus dn. Okay, c plus dn. In other words, that would mean that the sequence would look like a sub 0 would be c when n is 0, a sub 1 would be c plus d, a sub 2 would be c plus 2d, sorry, a sub 3 is c plus 3d, etc. Right? That's our formula for the nth term of the sequence, and that's what we'll try for the particular solution. I'm not going to clutter this up by putting a p up here at the top, but we'll understand that's what we get in the end. So let's try that and plug that in. So that would tell us that a sub n is c plus nd, or dn. A sub n minus 1 is equal to c plus n minus 1d. Okay? So let's put that into the recurrence relation above. I don't care which form we use, but I guess I'll use this one that we have over here on the right up there. Let's put it in that one right there. Okay? So that would say that c plus nd, that's the an right here, minus 5 times c plus n minus 1d, like so, and that's the 5an minus 1, is equal to minus 16n. And then we'll combine terms here and compare common powers of n. So if I look at this, this is c plus nd minus 5c minus 5nd minus, that's this term here, 5nd, and then there's also a minus 5 times minus 1d, so that's a plus 5d is equal to minus 16n. So let's collect the constant parts and the parts that depend on the variable n. And it's akin to what you would use in an earlier algebra course. You would use an x there for your polynomial variable, but here it's n, that's the polynomial variable. So if we bring these all together over here, we'll have the constant part then has c minus 5c, that's this part right here, plus 5d, and then the parts involving n are d and d minus 5nd, like so. So if we put those together, we're going to have plus nd minus 5nd is equal to minus 16n. So this is minus 4c plus 5d, and then that's minus 4nd. Minus 4, let me put the d in front. I didn't put the 4 there, sorry. Minus 4 d times n is minus 16n. Well, there's no constant over here. That is to say, there's a 0 there. These two have to be equal, as do these two right here. So let's deal with the ones I underlined in blue first of all, and that says that minus 4d, the coefficient of n here, must be equal to minus 16, and that means that d is equal to 4. And if d is 4, then that means that if I put a 4 in up here, I have minus 4c plus 20 must be equal to 0, the constant term. So this is the n coefficient, and this is the constant term, and that means that c is equal to 5. So our particular solution that will work here is a sub n superscript p is equal to, let's see, how do we write that? C is the constant there, that's 5 plus 4n, right, like so. And so we do get a linear equation that will work here. And by what we said last time about adding a homogeneous solution and the linear together gives us a general solution, we have now the general solution is equal to an. An is equal to alpha times 5 to the n, right? That's where we started off with this thing. And then plus 5 plus 4n, and that's the particular part. This is our ANH plus ANP, right? There's no initial condition here, so we'll leave it like that, and that's just our general solution. So let's look at one that's a little bit more complicated, just in the sense that it uses a quadratic. And I don't think I'll go through the full calculation of the solution here. I will let you try to do that, but I will give you the solution so you can work it out. So this right here, that's the non-homogeneous part. And what that would imply is that we might try a sub np equal to, let's do b plus cn plus dn squared, a quadratic. And by the way, you need all the terms in the quadratic, just not the ones associated with the powers that you see in the equation. And then, of course, a and h is equal to, from the homogeneous part right here, we get alpha times 4 to the n. Okay? So if you go through and substitute this into the equation, you'll get, and I'm going to leave it just like it is on that side right there. You get on the one side, on the left-hand side, you'll get b plus cn plus dn squared is equal to, so that's a n p, that's going to be 4 times a n minus 1 p, and so that'd be b plus cn minus 1 plus d n minus 1 squared. Okay, we've got a square there that's going to make it a little more calculational heavy, but nothing more than that, plus 6n squared minus n. So cleaning that up and equating powers, equate coefficients of the same power of n. That must be true when you have a general pair of quadratics or polynomials that are equal. Then doing that would give us the values. In this case, what we get is that b is -4, c is -5, and d is -2. Right now, what did we start with? We started with that form right there. Yeah. So our solution in this case would be an is the homogeneous, alpha 4 to the n, that's the homogeneous, plus the particular, and the particular one we found was -4 -5n -2n squared. So there's the general solution. In that case, it is our typical sort of solution plus a quadratic here. I could have written this differently without the plus and just have minus over here, but that's the way that one works out. I'm going to do a few more of these, but I think what I'll do is you can check the calculations on that last one to see how that came about. Let me just point out what happens when you have, instead of a polynomial over here, that you have some sort of a power. In this case here, if you have some sort of a power there, I'm going to rewrite that as an minus 4an minus 1 is equal to 5 times 3 to the n. So here's our non-homogeneous part. It doesn't have any terms of the sequence, the a subscripts in it. And so I think it might be helpful to understand that if we have a power of 3 as our non-homogeneous part, our particular solution, then an is going to be a power of 3, and an minus 1 will be also a power of 3. It's going to be a little lower power of 3, but by multiplying by constants, we'll be able to bring that up to the 3 to the n. In other words, in a situation like this, one thing to try is an superscript p equal to something like c times 3 to the n, a constant times 3 to the n. And if you put that into the equation here, you'd have an minus 1 super p would be c times 3n minus 1. And lo and behold, you put these into the equation here, and we have c times 3 to the n, that's our an, minus 4 times c times 3 to the n minus 1 equal to 5 times 3 to the n, like so. And we can cancel the 3 to the n minus 1. That's the lowest power of 3 here, so that'd be 3c minus 4c. The 3 to the n I'm canceling is equal to 5 times 3, or minus c is equal to 15. So c would be 15, and in fact that works fine. An p is equal to minus 15 times 3 to the n is our particular solution in that case. So a particular, or a power, tends to lead to a power for the particular solution there in a non-homogeneous part. I guess I should write down the general solution here is equal to some alpha times 4 to the n minus 15 times 3 to the n. That being the homogeneous part, that being the particular.